Hello friends, welcome to video number 18 of Data Structures and Algorithm Practice. You may be seeing a link below. By clicking on that, you can join these questions for practice. Let me introduce you about myself before we jump on to the question. My name is Akshaya. I am from IT Delhi, BTech Computer Science graduate, having worked at companies like Amazon and Paytm as software engineer and senior software engineer. And also my students being trained by me have handsome packages working presently at Paytm and Microsoft, and they were able to do so with the help of the special formula which I have. Okay, so you can click on the link and join in for practice. Basically, a question is posted and you are given the time that you'll be able to solve it by yourself. If you're not able to, you can always message me, right? And even after that, maybe after 24 hours period, if you're not able to solve it, you can watch the solution just like this video and be able to do it by yourself. Okay, so let's just jump on to question number 18, or basically the question number 4 for stacks. Okay, so basically the question talks about binary tree Inorder Traversal. Like I always say, always try to understand the question first. So let's try and understand the question. Never assume that you know things, because that's going to be the biggest obstacle on your way, right? Not even in just understanding questions, but also in learning. So always learn as much as you can, as deep about the things that you're studying. So let's dive in. Given a binary tree, return the in-order traversal of its nodes values. Okay, so some of you might not be knowing what is a binary tree or what is a tree and what are in-order traversal. So let me just explain that in brief. Basically, a tree is kind of a data structure, where data structure means how different kind of information is stored, right? So what do I mean by that? It basically means we all have different kind of information available to us, right? For example, let's take your room. Inside your room, you might be having different cupboard boxes, and inside the different cupboard boxes, you have kept different kind of belongings, right? And because you remember in your brain what is kept where, you're able to access them very fast, right? So if there was a new person who comes in, they won't be able to find it. They might have to open all the cupboards one by one, right? So, and similarly, the information can be stored, the belongings can be stored differently, like, right? For example, they can be just spread all across the room, right? Or they might be stored in a certain fashion, right? Depending upon the fashion they are stored, even a new person might be able to find the things correctly, right? So a data structure is also about that instead of storing the actual belongings of physical things, how do you store information in a way that you are able to perform operations like accessing it, modifying it, and things like that. And one of those data structures is a tree. Now what is a tree? A tree is like an actual tree. Imagine the root of the tree. Okay, don't imagine the tree, but imagine the root of the tree. If you see the root of the tree, it has many branches coming down, right? And if you follow one branch, you will reach to multiple more branches, sub branches, and these sub branches may lead to even more sub branches, and so on and so forth. So a tree also has the same structure. A tree data structure has the same structure, where you have a certain root from which branches are coming down, and on each branch there is another root like node which branches down sub further, right? So if you want to reach the end of one sub branch, what you will have to do, you will have to start from the top root node, right? That will be called a node. Then you will move down by one node, then you will move down by another node, and eventually you will reach the bottom, right? That's what a tree data structure is. Now what is a binary tree? Binary basically means two, right? So a binary tree is a data structure where each node, right, we remember the root node has multiple branches coming out. So in a binary tree, each node will have maximum two nodes coming down, right? So let's say at the top we have the number 1 stored, right? And then over here we have 2 stored, and over here we have 3 stored. Now when you take 2, this 2 might be having further branches. One is 4, one is 5, and so on and so forth, right? So that is a binary tree. You may probably Google upon it, or maybe look into the books which I had already given you for reference. If you are not aware, then you can join the group, or you can message me for knowing what that resource is. Okay, now what is an in-order traversal of a tree? So honestly, if you right now don't understand what a tree is or a binary tree is, it might be a too much of an expectation for you to be able to understand what is in-order traversal, but I will give it a try. Okay, in order. In order basically means following things in a particular order, right? So an in-order traversal goes like this. Okay, so when you normally travel a tree, when you're going down from the root to the bottom, how do? You first check the root node, right? Then you go to its subroot, then you will go to its sub branch, and so on and so forth. When you reach the end of the sub branch, you go back a step ahead, and then you go to the next sub branch, you travel it entirely, then you come back, and then you go on and move ahead, so on and so forth. In an in-order traversal, the order is that you move from left hand side to the right hand side. Okay, so first you're going to access the node which is on the left hand side, right? Because normally in most of the languages we start writing from left to right, right, except for a few exceptions, but most of the language we move from left to right, right? So an in-order traversal basically means like that you're moving from left to right and you will access the nodes in that order. So what this basically means is you go to the most extreme left node first, right? You travel it, then you go back to its parent, mark that parent that you have traveled, then you go to the rightmost node and then you travel the leftmost part of the node, and then you come back, then you travel the rightmost part, then you go back one level and you keep on going ahead, right? So that is a very small explanation on in-order traversal. You probably need to go through this reading material on this, so you can join the group and I will give you a lot of reading material for understanding this. So now let's move ahead. Okay, so I assume now the people who are watching this video understand every concept that has been covered till now, and now we are ready to understand how we can solve this. Okay, so this is a tree which is given. So you have 1, then the right child is 2, and then the left child of 2 is 3. Okay, so as I always say, take examples and try to understand, right? So I would demonstrate that taking example strategy in this video, because this video can actually go very long, because I think I have a lot of concepts to explain in this, and I think I will be explaining you multiple solutions also about to do this. So I won't go into much examples and I will directly jump onto the solution. So the question says recursive solution is trivial, could you do it iteratively, right? So recursive solution is actually very trivial, right? Some of you who have done even a few example problems in recursion should be able to do this problem very easily. But that said, recursion is a very important concept and has a lot of small basic things that you must understand while doing a recursive problem. So much that a problem like this you should be able to do in your head maybe in 1 or 2 minutes only, right? That is the speed that you want your recursion to be there. But because this video is not about recursion, I won't be sharing details about how you can build upon that, but I will explain the simple solution of recursion directly over here. Okay, so for that let's take an example and see how we can do that. Okay, so let's draw a tree node. Okay, this is the root of the tree node, and this will be probably the left side of the tree. If you are watching the video inverted, then things left and right might interchange, but I believe that won't be the case. Okay, so let's say this is the root of the tree and this is a left subtree and the right subtree, right? So if you want to traverse this tree in an in-order traversal, what you need to do? You need to do an in-order traversal of this left side of the tree, then you need to visit this root node, and then you need to do a recursive traversal of the right side of the tree, right? And you should be able to mathematically prove that if you do that, your solution gets solved, right? Again, that can take maybe actually 3 to 4 hours to actually explain all the basics of that, so I won't go down that lane right here, but I will just implement the solution and explain you along. Okay, so how do you actually do this? To save upon the time, I've already kept the code ready, so I'm just going to copy paste the code Okay, I'm just going to copy paste the code and I'm going to explain you what we are doing over here. Okay, and I have multiple solutions ready to explain to you. Okay, so the first thing is that we are going to solve the problem using recursion, right? But if you look at the question is already giving you a signature of the function that they want, right? They have given you a list as an output and they have given you a root as an input, right? Now, to be able to do this recursively, it won't really be possible because there's no way to pass on the current position of the list, right? How the list has been changed, or where do we need to add the list, that's not there, right? That's why I'm going to use a design pattern over here, which is all about a helper method which is recursive and which will be called and which will perform the actual recursion and will perform the things, right? So over here I've defined the list L, linked list, which is basically the answer. So now we can modify this and I'm going to pass this L in my recursive function, which is helper. Now helper takes in two inputs. One is a root of the subtree or the tree on which you want to perform this operation, and you will do an Inorder traversal and you will add the Inorder traversal into the list, right? So remember, in this example what we were doing, the recursion of Inorder traversal on the left subtree, then we were performing the operation on the root node, and then we were performing the recursive operation on the right node, right? So over here we need to pass in the list, right? That's why I created the linked list over here. Okay, now let's see how the helper function goes. The helper function, as I always say in recursion, we have the solution assumed and we will apply recursion assuming that it works for smaller solution, and then we will use it for bigger one, right? So when you are given a tree node and you are given a list L, what you need to do is you need to assume that this solution will work for smaller subtrees, right? This helper function is going to work on the smaller subtrees, right? So let's just do that. If it works on a smaller subtree, then I can directly say that L is equal to helper applied on n dot left comma L would basically mean n dot left being traversed in an Inorder fashion, and L is the list which gives the Inorder traversal, right? Then I will do L dot add and dot well, right? Basically the left subtree has been traversed, its Inorder traversal has been stored in L, and the root's value has been appended towards the end by this, right? And once that is done, the right subtree is left, and again what we have to do is basically we have to pass the right subtree's root node, and we have to pass the list that we have already got. So we will get L over here being passed, and then the result that we are going to get is going to be a complete Inorder traversal starting from the left subtree, the root, and the right subtree, right? And as a result you will get the answer directly, right, written in, and this works perfectly well. Let me just run this code and show you the solution also. And as soon as we do that, I will actually move on to very interesting ways of solving the problem so that you can apply this in different places very easily. Okay, not just this question but others. As you can see, this code runs very fast, 100%. It works faster than 100%. Even though it's recursion, it's working really fast. Okay, so let's try and analyze the time complexity of this. Okay, so as you can see in the helper function, the number of operations which are taking place, this is basically order one operation, and then this kind of function is being applied on the left side of the tree, and this function is being applied on the right side of the tree, right? So I guess to explain this recursion problem, we will have to form a recursive formula, something like T of n, right, where, or T of h, okay, T of h, where height, h is the height of the entire tree, T of h is equal to T of h minus 1, right, plus 1 plus T of h minus 1, right? Both left and right are going to have an h minus 1 in them, right? And when you are going to solve this recursive pattern, you will get t of h is equal to 2 times t of h minus 1 plus 1, right? And when you will go down again and again, you will reach t of h is equal to 2 to the power k, 2 to the power k into t of x. Now I'm just leaving that as a hint to you to think of what is the relationship between x and k. If you can figure out that relationship, you will be able to figure out the time complexity for this, right? So please do that, and below you can drop the comments and let me know. Okay, now let's move to the to a better solution, or maybe not a better solution but an iterative solution, right? Even the question had asked us to do that. Recursive solution is trivial, could you do it iteratively? So let's try and do this iteratively. Okay, so I've already the code ready for that, and this iterative code is pretty much easy. Okay, pretty much easy to understand. After we are done with this second solution, which is the iterative solution, I will take you to the real important solution for which I think the I am creating this video for. Okay, this third solution which we are going to deal with after this solution is going to be applicable in probably all kinds of questions, and you can solve all kinds of problems, okay, using that technique. Okay, so this is the code for an iterative traversal, and before we can understand this iterative traversal, let's take certain examples and see how one can approach or come up with that kind of solution. So let's say this is the only node in the tree. What is going to be the in-order traversal? It's very simple. You just add this node's value to the linked list and you will be done, right? Now let's say what happens when we have a tree of height 2, right? So in that probably we will have let's say only the left node. If you have only the left node, you go to this node, right? You mark, you do the traversal on this, that is add this left node to the linked list L, and then you go back to the parent, right? That would be sufficient. Okay, now let's take another example. If we have a tree like this, what you will do, you will first add this to the linked list, right? And then you will go to this and you will be done, right? Now let's say what about this. In this video I am moving pretty fast, traversing different kinds of node. You, when you do by yourself, take your time, try to understand things. I am doing that so that the video doesn't be too long. Okay, so when you add this node, to do an in-order traversal, you have to first go to the left node, right? You will do the mark this node as traveled. You will add this to the linked list L, right? And once you have done that, you will come back to the parent, right? You will mark this as done, that is adding to the linked list L, and then you will go to the right child. This will ensure that there is a in-order traversal. Very good. So these questions do seem simple, and it seems like we first go to the left child, then we come to the parent, go to the right child. It's quite obvious, right? But let's take a bit complicated example, because that's what is going to help us understand what approach we are going to apply if we want to avoid recursion. Can we probably come up with some approach which will be applicable all the time, right? Can this problem actually be done without recursion? Okay, but let me share this with you. If you have any problem which you can do with recursion, then theoretically speaking it can be done by iteration, because recursion is same as iteration in a way. Okay, so what I'm saying is basically you can create your own stack and kind of simulate the same recursion thing on that stack, and you will be able to solve the problem as iteration, right? How does a computer program implements recursion? The computer at the back, how does it implement? It does have no knowledge about recursion. What it does is it does simply perform iteration only, right? So if you have already a solution which is being done in recursion, all you have to do is convert all you have to do is basically simulate the same process that the computer's backend machine implements to implement the recursion thing, right? It's basically same as iteration. Okay, so let's try and do this problem, right? So if you want to do an in-order traversal on this root node, you have to first do an in-order traversal of the left node, right? And now for this left node, if you have to do what you do, you basically have to do the in-order traversal for its left node, right? And for this, you don't have any children, so simply you can say this is traversed and you are fine, right? And now what you have to do, you have to go back, right? You have to go back, right? So because it is not recursion, how do you go back? You don't have a pointer to the parent, right? You don't have a pointer to the parent, so you cannot go back, but you can store the information a certain way. And this, when you identify that you have to store the information in a way that it's last in first out, which is like a stack, you will understand that probably I can store the parents in the stack, right? Because when you come to this node and you are done, you need to go back to this, and after doing this you need to go back to this, right? This is something like a stack, right? The node which was inserted, the node that we came last across, will be on the top of the stack, and the one which came before that will be the next element in the stack, right? That's why we are going to use a stack. It gives you a slight hint. Okay, so once you have traversed this, what do? You go back. And how do you go back? You go back with the help of a stack. On the stack you would have pushed this information. Now when you come back over here, you must make sure that you remember that you had already traversed the left side of the tree. Okay, you have already traversed the left side of the tree, because otherwise you will be caught up in an infinite loop that you will go to the left will go to the parent, then parent goes to left, and so on and so forth. Okay, so let's assume you have identified some way to know that the left side has not been traversed, right? So when you are over here, you already know the left side is traversed. So as a human, what do? You go to the, you mark this node, being added to the linked list, right? The answer of the linked list, and then you go to the right side. Now once, and this is also marked done, right? This is also marked done. When you move to the right node, again the same thing happened. To be able to do this traversal, you have to first go and mark the left child, right? So that's why you go over here, you mark this left child to the linked list, and then you come back to the stack, you pop that element so that you get this parent, and when you add this parent, you mark this one as done, right? You mark this one as done, you add this to the linked list answer, and then you go to its right child. And to be able to do this right child, you need to go to its left and you mark that as done, that is being added to the linked list. Then you go back to the parent, mark this is done, right? Now when you are this position, right, you have identified that its left and right children are done. Now you probably need to go back upward, right? And we know that we don't have a pointer to the parent, right? But we know the ancestors of this node might be present on the stack, right? Because if we are at a node whose parent has not been traveled, it would definitely be on the stack, right? If there's no node present on the stack, it basically means that everything has already been traveled, right? You may have to think a lot on this one probably, but if you will take examples, you will stay with me. Okay, so when you are at this, you need to go to the parent, right? Now this parent was already taken care of, right? This parent was already taken care of when we popped it, when we went from this node to this node, right? And even this node was also popped up when we went from here to here, but this one will be still on the stack, right? So from this node we will come to here, right? From here we will actually, yeah, so from here we will reach this node, and when we reach here we will mark this to the linked list, right? And then we will go to its right child. When we reach this right child, we know it doesn't have a left child, so we can mark this as taken, right? And then again we will go to the next one and again mark this as done. And when we come over here, we will understand that the stack is empty, so we will be done. Okay, now let's come, how do you make the computer do so? Okay, how do we make the computer do so? I would still recommend you to take more and more examples so that you can understand what I'm trying to say. And if there's any confusion, maybe watch the video again and try more examples, watch the video again, and you will get it. Okay, so there's a very important observation you must have when you are doing this, and that observation is that we need to pop the stack, right? The parent of a node has not been done only when we are moving from the left child back to the parent, but while we are moving from the right child back to the parent was already done, right? For example, when we are moving from a left child back up, the parent wasn't done, that's why it was on the stack, right? When we will move from this to here, again the same thing, because it's a left child, that's why the parent is there. But as soon as a node's right child has been done, it must have already been removed from the stack because it was already done, right? For example, when we are moving from here to here, right, we already know that this was done. When we are moving from here to here, we know this was done. When we are here, right, and when we are moving up, this is still part of the left side, right? And that's why this node was there. Okay, bit tricky over here, but let's see the code. Maybe that will help you understand it better. Okay, so I've defined a stack of a tree node, right? Because we understand from our own examples that we need a stack, right? And this is the linked list of integers which is basically being asked in the answer. Okay, so if root is equal to null, return answer, right? If the tree is completely empty, we don't need to do anything, right? So simply you can return an answer which is basically going to be an empty linked list and you will be done, right? But what say if the root is not null? Then we are going to play that game. Okay, and let me explain you what the game is. We define the tree node temp is equal to root, okay, and then we are going to push the nodes iteratively till we reach the leftmost side of the tree, till we reach the leftmost node of the current root. We are not going to stop. Okay, so this is what it is doing. My stack dot push temp, then temp is equal to left, right? And if the current left is not equal to null, then we will again push, right? So let me show you with the help of the diagram what we are basically doing. Let me just draw over here, right? So let's say this is the tree. Okay, so what we are doing is, because this tree has a left node, this root has a left node, we will push this onto the stack, right? Now we will come to this also has a left node, so we will push this onto the stack. Now because this also has a left node, we will push this all onto the stack, right? And when do we stop? We stop when temp is equal to null, right? So till the time even this is not pushed onto the stack, we will keep pushing, right? So basically we will push all the nodes onto the stack till we get the leftmost node, right? And when this stops, we know that the top of the stack is going to the leftmost node, right? Now this is a very interesting thing to do. The reason for that is, when we do this, we identify and we know that the left nodes of all these nodes have been taken care of, right? Because let's say when we have dealt with this node and we come back to this using stack.pop, we know that this left node is done, right? And we won't go down, but we may check what is happening on the right side, right? And when we are checking on the right side, again we are going to do the same thing. Okay, let me explain. Let's say we have done this node completely, this subtree completely, right? And when we come over here, we mark this as traveled into the linked list. And when we come to the right node, again we are going to do the same thing. That let's say if this right node had left child, and this also had left child, and this also had left child, so we are going to iteratively push all of them onto the stack. So again the same condition or kind of the loop invariant is maintained, that we get the next leftmost node of the tree, right? So you will see in the code that after I have run this loop, this is like a starting condition. I have got the leftmost node of the tree. Now in this, the second while loop, okay, the second non-nested while loop, I'm going to do the same thing. I'm going to pop the topmost node, which is going to the leftmost node, right? I'm going to travel it. I'm going to see whether it has right node or not. If it has right node, I'm going to again recursively apply the same thing. But if it has no right node, I'm going to travel and mark this one, and then I will pop the next node from the stack and repeat the same process. Okay, let's see. So as I said, I will pop the stack, which basically gives me the present leftmost node on the tree, right? We need the leftmost node. And then in the ans, we are going to do ans.add and dot value, right? Good. Now what we are going to do is n is equal to n dot right, right? So we have got a new node and basically a new subtree, right? New subtree, and we are going to find the leftmost node on the tree. The solution of this problem lies in this only, that you find the leftmost node and travel that, right? If you can always find the leftmost node in the given subtree, you know which is the next node, and if you can iteratively do it again and again, you will always have an Inorder traversal, right? So over here again, we are doing the same thing, right, which we had done over here, right? You will see till n is not equal to null, I am going to push my stack dot push n, and n is equal to n dot left. This code is exactly the same as this one, right? These two codes are exactly the same, except that n is become n dot right. Okay. Now when we do this, again we have by definition that on top of the stack we are going to have the leftmost one, right? This question might become bit confusing, right? And that's why it is very important to be strong on mathematics and proof skills and problem solving skills, so that all the computation that I'm presently doing in my head, you should be able to do that. Because in an actual coding interview, the time which will be given to you would probably be like for 2 hours will be given for probably 4 questions for an online coding round, right? And when you are given 30 minutes per question, doesn't mean you take all 30 minutes. Ideally, you should be able to think of that solution, implement it in 10 minutes, right? And the next time, rest of the time will be taken in proving it or identifying certain bugs. Okay, and when you are giving an actual interview, probably the interviewer will discuss with you, and after he or she has explained the problem to you, you should be able to come with the solution in maybe next 5 minutes, and you should be able to explain them mathematically also, right? That's why I'm saying it is very important to master these basic concepts so strong that you can do the computation in your head, right? Okay, so this will happen and you will get the answer. I will explain the solution once again, but let me just submit this and show that this is also working. Great. So it is also working so fast. It is working. It is running faster than 100% of the Java online submissions, right? That said, I would also like to point out, don't rely on the speed which is given over here, because this may sometimes depend on the size of the input, right? Always emphasize on computing an asymptotic analysis of time and space complexity, because that is a real determinant of how your code is going to behave for bigger input sizes. Okay, so let me explain to you the algorithm once again. What you basically need to do is, for an in-order traversal, always find the leftmost node in the tree, add that to the answer linked list, right? Then go to its parent node. Okay, add that parent node also to the answer list. Now see if that parent node has a right node or not. If there's no right node, then you can iteratively go upwards. But if there is a right node, this means that instead of the current parent's parent as the next leftmost node in the tree, the left children of the right node of the present node might be the leftmost node, right? You may actually pause the video and watch the last 1 minute again to understand what I just said. Okay, so you go to the right node of the present node, and then you find iteratively the leftmost node by running this while loop. You will reach over there, right? You will reach over there, and then you will travel that, and again iteratively you will do the same thing. Okay, I understand this problem is pretty tough, right? Especially for people who have not cleared the interviews or who wouldn't have given so much time in understanding the basics, and someone who has not practiced. But sooner or later, you will catch up. Okay, focus on understanding the basics and giving a lot of time into that. Now let's try and understand what is going to be the time complexity. Okay, now there can be a lot of methods of identifying the time and space complexity, right? Some of them will be useful in some codes, some of them might not be useful in those codes. For that you will need different techniques, right? So recently I had shared a very simple technique in the group, where I defined how do you find the time complexity. That is not perfect, but it is applicable at certain places. Similarly, over here I'm going to give a very simple technique, okay, very overview kind of a technique, but make sure you understand all the ifs and else about it by doing the computations in your head like I'm doing right now, so that you can apply it right at the right place. Okay, if not, you can probably join my course and develop that thinking. Okay, so n is equal to n dot right while n is not equal to null. This is basically a while loop running inside this while loop, right? And if you apply the philosophy or the formula, how do you compute it for a nested loop, you might get stuck up, right? But if your mathematics and proving ability are strong, not just intuitively, but mathematical ability is also strong, you can prove that each node each node in the linked list, each node in the tree is going to be pushed into the stack only once. Okay, it does seem intuitive over here, but I'm telling you there's a mathematical proof also to for being able to do so. But if you will get into that, probably it will take 2 to 3 hours to do so, right? Because it's going to like explode. So I'm just giving you the intuitive answer right now, right? And I want to shift to the next solution, which is going to be more important, right? We can be sure that each node is being pushed onto the stack only once, right? And whenever a new node is being coming up, maybe through the stack or through otherwise, we are going to perform order one operations on that. Okay, that is actually probably not true. Okay, that is probably not true, but we can understand that each node is being inserted into the stack only once, and all the operations are basically about pushing and popping, and all operations other than pushing and popping are order one operations, right? So you can say that if there are n nodes in the tree, the time complexity is going to be order n, right? And what about space complexity? The space complexity, you can also say it's order n, but a tighter bound on that is going to be the height of the tree, right? You can actually prove that it's going to be the height of the tree, and it is a stronger bound, stronger upper bound on the space complexity. Okay, and the computing the space complexity also has a very specific method, very mathematical method. The interviewer might ask you and question you how you do that, right? And if you don't have that problem solving ability, if you don't have that mathematical proof with you, the interviewer will reject you, because they will know that this person is giving that answer by fluke, because it's an intuitive answer but the person doesn't know for sure. Second thing, you will also won't be confident in the interview, right? If the interview asks you the answers, until and unless you are sure, right, you may not speak up. And even if you speak up and the interviewer, just for testing you, says that your answer is wrong, you might probably either end up arguing. Even when your answer was wrong, you might end up arguing with the person that answer is right. Or if your answer was correct and the interviewer says that your answer is wrong, you may still end up arguing, but with wrong reasons. What actually will matter in the interview is not about argument, but giving a logical answer which suits you as well as them, right? That's why it is very important to have that clarity of mathematical thinking in your brain and being able to communicate that. Okay, now let's move to the very special solution that I had been talking about, which I wanted to work upon, share with you, because it's going to be useful wherever you are going to use it. Okay, this kind of a solution, I think I have probably shared earlier also. I'm sharing it here again to help you understand. Okay, so for this, let's try to understand what we are going to do in the code. Okay, since I have already have the solution, it will be very easy for me to put it forward to you, explain to you, though it's very hard to understand the problem and to be able to explain the solution to someone who is just learning, right? It can actually take time, but I have written down certain statements on my copy which are going to help me explain to you. There might be certain mistakes, but when we will come to the code, the mistakes will be overcome. Okay, so let's start in this way. Let's say, should I write it down or should I draw it? Um, I think a better way would be to draw it. Okay, so let me draw it for you. We had actually applied this earlier also. Okay, so let's say you have a node. Okay, and that node is start. Whenever you come across a node, what do? We want the leftmost node, right? We want the left node, right? So you're going to check whether the left node is going to be null or not, right? You're going to check whether the left node is equal to a null. Okay, I'm going to write a null with the help of a cross. If the left node is going to be a null, what do? I basically add s to the solution, right? Let me actually write in text to explain better. S dot left, if s dot left is equal to null, what I'm going to do is I'm going to do L dot add start, right? If the left node is there, is not there, I can directly do the traversal for the current node, and that's why I'm going to add it to the linked list, right? Now there are two possibilities which are left. Okay, one possibility is if s dot right is equal to null. S dot right is equal to null. Okay, we already know that the left node is null, and if right is also null, then we know that the traversal has been done, right? The traversal has been done, and for some time let us keep it like that. Okay, now let's say, what is the other possibility? The other possibility is s dot right is not null. If s dot right is not equal to null, then we will basically have to do the traverse on the right node, right? And what we can do is, okay, so to be able to proceed, I think I probably will have to share this thing with you, that we will get two kinds of node. One of the node we are going to get from the stack, and one of the node we are not getting from the stack directly, but we know. Okay, let me put it this way. So there are basically two kinds of node you are going to come across. One of the nodes is such whose left nodes have already been taken care of. Okay, the other set of nodes are going to be ones for which the left nodes have not been taken care of. For those nodes for which left has been taken care of, we can basically traverse this node and then we can move to the right, right? But for those for which left has not been taken care of, we will have to push the current node onto the stack and deal with the left nodes, right? And because we are putting this thing on the stack, we have to ensure that when we are popping this node from the stack, we again don't go on to the left side, right? So that's why it is very important to differentiate between these two kind of node. One node which is coming from the stack and one node which is not coming from the stack. Those which are coming from the stack, we will not go on the left side, and those which are coming without the stack, we will have to check the left side also. Okay, so let me write down the condition. Let me just write down the other one also, which is coming from the stack. Okay, this is this as, okay, let me just write this with the text. This basically represents not from stack. Okay, this is coming not from stack, and this node is coming from stack. This node is coming from stack. Okay, so if the s dot right is equal to null, if s dot right is equal to null, this basically means this node is done and we will have to pop the stack, right? So that's why you will have to go to this one. Which one? Which we are getting from the stack, right? So s is basically going to be, basically we are going to pop the stack and see what is our current node. What is our current node, right? And if left and the right is not equal to null, this will give you the answer that what kind of nodes are not going to come from the stack, right? We will, for example, over here we know that right is not equal to null, so we are going to say that s, we are going to say that s, okay, we are going to say that s is equal to s dot right, right? S is equal to s dot right, right? And we would have already done L dot s, L dot add s, right? Or we had actually already done that. As soon as s dot left was null, we have already done that. So we will do s is equal to s dot right, and then we will again come back to the same state. So if you get any node which is not from the stack, this basically means you have to take care of the left one also, right? So you will see if s dot left is null or not. If s dot s, if s dot left is equal to null, this basically means you can add the node, the current node, to the linked list answer, right? And then you will have to deal with the right one. If the right one is already null, this basically means the next node will come by popping, right? So you will move to the state of conditions where you're getting the node from the from popping, and that's why you have to take care of the left node also. But in case the right is not equal to null, you will directly say s is equal to s dot right and move to this state of condition where you will have to deal with the left side also. Okay, that said, still one thing is left. What happens in the case, so arrows like this, what happens in the case when s dot left is not equal to null? That condition we have missed, right? So basically what is the condition over here? What do we do if s dot left is not equal to null? Then we will have to deal with it, right? And how do we deal with it? We actually going to do the same thing, right? When s dot left is not equal to null, we come to the left node, right? And we will perform the same thing that we did with this parent, right? If s dot left is not equal to null, we are going to do this thing. I am writing down over here below this. Push s to stack, right? Push s to stack, right? And then s is equal to s dot left. And after doing this, go back to the same state. Okay, go back to the same state. Probably I made some mistakes over here, but when we will go to the code, things will be rectified, right? So there are two kinds of node, one which you are getting not from the stack and one which you are getting from the stack. Those which you are not getting from the stack, you will have to take care of the left ones. Those you are getting from the stack, you will not take care of the left one because it will lead to an infinite loop. Okay, so let's see how we deal with something which is not coming from stack. Something which is not coming from the stack, we have to take care of the left side, right? So let's take care of that. Either the left side is going to be null or it is going to be not null. So there's no other case possibility. That's why we have taken care of this case completely. Let me show what happens when we have s dot left is equal to null. When s dot left is equal to null, we come down and we add to the linked list s, right? And then we check whether the right node is null or not null, right? Null or not null. If it is not null, I will assign s dot right equal to s and we will come back to the same. And if s dot right is equal to null, we understand that we need the next node which will come from the stack, so we are going to pop and do it, right? The other condition which was left was if s dot left is not equal to null. If s dot left is not equal to null, then we will have to take care of that. And how do we take care of that? By pushing the s node onto the stack, right? And then we move s is equal to s dot left, because if this is not coming from the stack, we will come to this state. Okay, great. Now let's come to the state of conditions for a node which we are getting from popping, right? So in this state, what we are basically doing is we are going to say s is equal to stack. Let me just write this with the help of a text. What we are basically going to do is s is equal to stack dot pop. Okay, that's the only thing that we are doing over here. Now we won't take care of the left hand side, right? And that's why we can directly do this thing. We can directly do l dot add s, right? In the linked list we can directly add the current node because the left node is already traveled. So in order traversal, the current node will come, and now the only thing which is left is the right node, right? So now let's check the condition for that. There will be two conditions. One which says s dot right is equal to null, s dot right is equal to null, right? And the second condition would be s dot right is not equal to null. Okay, let's say if s dot right is equal to null. If s dot right is equal to null, we understand that s is done, right? Because left side was already taken care of. S was added to the solution previously, and right is null. So we need the parent, and the parent will come by popping, right? And that's why over here we will go directly to this part, right? Because something which is being popped, something which is coming directly, the left side was already taken care of, right? Remember, whenever we are pushing something on the stack, we had already taken care of the left side, right? Great. So now this condition is left. What happens when s dot right is not equal to null? Now when s dot right is not equal to null, we will have to take care of this node, and this node is not coming from the stack. This is a completely fresh new node, and that's why we'll have to take care of the left node of the right node, basically the left node of s dot right? And that's why we will have to move from over here to over here. But before we do that, we will have to do this, that s is equal to s dot right, s is equal to s dot right? And from here we will move to this. Okay, this is the explanation of the entire thing that we are doing. Okay, now without dealing further, okay, let's try to keep the video short. Let me show you the code for this also, for how we are doing this in the code. The same thing which I just explained to you is the only thing that I'm doing. Okay, so let me just explain. So first of all, we created a linked list, which is the answer which is being demanded, and then we created a stack of tray nodes, okay, in which we are going to basically push those nodes which have left nodes and which we are going to take care. Okay, and then we defined iter is equal to root, and if iter is null, then we can simply return the linked list, empty linked list, because the Inorder traversal of a null node is nothing, is emptiness, right? Okay, now I'm going to run a while loop. Okay, so why I'm running a while loop on these two conditions? As you can remember from the diagram, we were getting nodes from two ways. One was we were getting directly a fresh node by the pointers, or we were getting it from the stack, right? So these are the only two ways we are going to get. That's why our looping condition would be either the iter is not equal to null or my stack is not empty. Okay, both of these conditions, at least one of these conditions should be true. Okay, now I am going to run an if else thing, and what this if else thing is basically doing is, this is basically checking whether a node is fresh. This iter is not equal to null basically represents that the node is fresh coming out from pointer, and this else part is basically representing a node which is coming by popping the stack. Okay, so if there's a node which is coming fresh, what do we have to do? We have to take care of the left node also, right? So that's why I created this if part, which is first taking care of the left node, right, checking if it is null or not. If let's say that the node is null, if the left part of the node is null, remember from the diagram what we used to do. If the left was equal to null, then we will add the node to S and then we will check for right. So if the left is equal to null, I added l.add iter.value, right, and then I'm doing a check for the right node whether it exists or not. If the right node is equal to null, then I'm sure that the current iter which was there has been traversed, and then I will need to pop from the stack the parent node and get it, right? So in this way, in this one, what I'm going to do is I'm going to assign iter equal to null. Okay, why I'm assigning iter equal to null? So that this condition of if iter is not equal to null becomes falsified, and that's why the code can enter this one, which is basically taking care of iter is equal to pop, right? And we need to pop this up, right? That's why I return continue, so that it directly exists this current iteration, and the next iteration it jumps over here. Great. Next, if the iter.write is not equal to null, then I will have to take care of that, right? And it is going to be a fresh node. That's why I want it to continue to stay in this if condition, right? So that's why I just did iter is equal to iter.write and continue, and because iter is not equal to null, it is going to come in this if. Okay, bit confusing, but write down in this paper and try to work out the what I'm trying to say, and once you figure that out, things will become very easy. Okay, always work on the basics. That's why I would actually suggest try working on this solution which I gave to you, maybe 4 to 5 hours. Okay, it might actually take you 3-4 days also to understand, but do that. That is very essential, because it's going to help you in getting the solutions for other problems. Remember, it's not about memorizing the solutions, it's about understanding how to do. Okay, great. So if this condition is not true, which is iter.left is equal to null, you will come to this condition where iter.left is not equal to null. When left is not equal to null, you will have to delete it, and it's a fresh node, so you want it to come over here, and that's why you will push the current node into the stack so that you can come back to later, and you will say iter is equal to iter.left and continue, and because iter is not equal to null, in the next iteration it will come over here. Okay, great. Now let's come to the second part of the code, which basically deals about nodes which are coming from the stack. The nodes which are coming from the stack are basically which are actually were pushed on the stack some time ago, and only those nodes which are being pushed on the nodes which are being pushed on the stacks are only those for which the left child had already been taken care of. Okay, and I can myself understand how complicated the things are when I am trying to explain the solution to you, right? Because there are a lot of things which I am computing in my head and trying to explain, because you don't understand the basics. So if you don't understand this one, it's okay, it's perfectly okay, don't feel bad about it, but make sure that you work on the basics. Okay, make sure, because time is passing away, so it is very essential that you understand the basics. Probably join the courses and you can understand things better. Probably follow the books that I have given to you, but even that is going to take you probably 3, 4, 6 months, 1 year if you try to do it by yourself. So come up ahead and take my help. Okay, so let's come to the else part of the loop. The else part of the loop basically says and refers to those nodes for which left child has already been taken care of, right? So that's why you won't consider the left anywhere, right? As you can see, I'm checking the right node only, right? So I get iter is equal to myStack.pop, right? Because left side is already taken care of. I'm doing l.add iter.value, right? And then I'm checking the right nodes. If iter.write is equal to null, if iter.write is equal to null, this basically means I'm done and I just need the parent node, right? And for the parent node, I need to pop the stack, right? And for that, I wanted to come back to this else, right? So that's why I'm going to assign iter as null. So you will see I assign iter equal to null and continue, so that our code exists this iter is not equal to null and can come into this part. Okay, the second condition is iter.write is not equal to null. If iter.write is not equal to null, I will have to deal with this just like a fresh node, and I want this to come over this loop. So what I'm going to do is I'm going to do iter is equal to iter.write and continue, right? And then you will run the code and return. Okay, and this will work. Okay, let me just submit the code and show you that it's working as well. Great. Though it's taking a little bit more time, but this kind of an approach will be very useful to you in online coding rounds, right? Because this is like a brute force way of solving things. This is going to be available to you all the time. Probably in an interview, this might not be so much useful, but for getting online coding rounds clear, or maybe to impress the interviewer, not from the point of view of being able to solve the question, but by showing that you can think of different ways of solving, this is a brilliant approach. Okay, this is a brilliant approach, though not the best one. Okay, because each question that you are going to do are going to have a best way of thinking for them. This is a new technique which I am teaching you right now, which you can apply anywhere, right? So if you do the time complexity and space complexity, this is much more easier to analyze, right? In this, each node is being traversed once, right? And when you're traveling it once, you might come across it again. And when will you come across it again? When it is being popped from the stack. And each node is going to be popped from the stack only once. Why is that? Because it is going to be pushed into the stack only once. And how did we ensure this? Right now you will say it is very intuitive, but let me just present to you the actual thing. This code is very tricky, right? When you will do mathematically, you will understand. And let me put that forward also to help you understand why I'm saying so. Remember, we are avoiding an infinite loop in the code. How we are avoiding that infinite loop? By ensuring that left node, that whichever node is being pushed into the stack, we remember that its left node was already done. If we would have not ensured that, then we will be caught up in an infinite loop that we come to a node, we push that to a stack, we deal with this left node, then we pop and get back the same node, then we again do the left node, we deal with it, then we again pop the node, we come to the node, then we push that back to the stack, come to the left node, and again. So there will be an infinite loop, right? But if you can prove this mathematically in this one, you will understand that this doesn't have an infinite loop. Okay, so because of that, the time complexity of this is probably going to be order n or order 2n, which is same as 2n, and the space complexity is going to be same as order height of the tree, as I explained previously, right? So this is how you can do this problem. I hope you learned a lot. Keep liking, commenting, and subscribing to the videos, right? If you have any kinds of doubt, please feel free to mail to me, drop down the comments, drop down what is the number and insight that you got from this, so that I can understand what is my blind spot of assumption, which I think is being understood by everyone, right? Because I have been doing the problems myself for a long period of time. I might be having certain assumptions and believe that this is quite obvious, but might not be, right? And if you have other ways of solving the problem, please drop down the comment also, right? And because unless and until you drop the comments, I'm not sure if you're watching this and what part of the video you're liking, and I may not be able to emphasize that in the future, right? So I want you to right now click on the like button, I want you to click on the subscribe button and drop in your comments. Okay, so we will catch you in the next one. Don't forget to click on the link and join the group for practice. Bye bye, take care.